Welcome to State of Simulation, the podcast all about multiphysics simulation, where we stay up to date with what's working, what's not, and what needs to change. Each episode features an open conversation with the engineers and technical leaders shaping the future of physical product development. I'm your host, Jukka Knutinen, and in today's episode, we're speaking with Tommaso Bagni, Superconducting Magnet Engineer at Gauss Fusion. With over a decade of experience in applied superconductivity and applied physics, Tommaso works on developing the superconducting magnets that sit at the very heart of fusion reactors. His focus today is on creating demountable superconducting coils, a new approach aimed at solving some of the toughest manufacturing, transport, and maintenance challenges in fusion power plants. In this episode, we talk about how simulation supports the design of these complex coils, from electromagnetic and thermal analysis to quench protection, and what's still missing in today's tools. We also explore how Gauss Fusion is tackling industrial scale challenges, where AI and machine learning might help in the near future, and what signals to watch for as fusion moves closer to reality. Without further ado, let's get started. What is Gauss Fusion building?
So Gauss Fusion goal mission is to accelerate the industrialization of fusion in Europe in order to achieve the construction of a fusion power plant by the 2040s. And our goal is to build a fusion power plant based on magnetic fusion confinement, based on the stellarator technology.
And for those new to the topic, what role do superconducting magnets play in this fusion reactor, or more specifically the stellarator?
So when we talk to magnetic confinement, is already in the name. The coils, the magnets plays a fundamental, crucial role. They are responsible to create a magnetic field, a very strong magnetic field, capable to contain the fusion plasma, because the plasma that is going to create in the power plant reach hundreds of millions of degrees Celsius. So basically, they would destroy anything that the plasma get in contact with. And so since the plasma is a charged gas, you can use a strong magnetic field to contain it, and so to make it feasible to be used in a confined space and used to produce energy.
So how is then your approach different or unique compared to others in the same space?
The magnet approach, the coil approach, is to base the technology on superconducting cables, superconducting materials, which are, just in brief, a very special material that if it is cooled down below a certain temperature, very, very low temperature, 5 to 20 Kelvin, the material drop the electrical resistance, and therefore you can transport a lot of current within the coil and reach very high magnetic field. So the complexity in a stellarator machine is for the magnetic system is very high, because most of the people can connect a coil or a magnet in something relatively planar, like a wind of a wire that generates a magnetic field. When we go to stellarator, the winding, so the coil, is 3D shaped, so it's very distorted. And therefore, when we scale up the technology, so we go to tens of meters as the dimension of the coil in the perimeter, the complexity to realize it becomes very high. There is a manufacturer complexity, because we are talking about 30 to 40 meters of perimeter of cable that you have to wind. Then there is the transport complexity, because we have to move pieces that are hundreds of tons. And so far in the stellarator technology, usually these coils are contained in stainless steel cases, so like a box that contains all the wire, and that when you have to move again hundreds of tons of material, and to move it, to put it in place around the fusion power plants, it becomes very challenging and very complex. So Gauss Fusion solution to this multiple complex problem is to build a new type of coil. So a coil that are called demountable. So it's a coil that is not a continuous winding, but is a coil that can be open and separated in pieces, so that the unit piece is a lot lighter to be moved, transport, and built. And this will solve a lot of industrialization problem, and because it's easier to manufacture, and also allow maintenance and repairing process on the coil and on the internal component of the fusion power plant. Because if you can demount a coil, it means that you can change just one piece of it if it breaks over the 40 years of operation, instead of having to change the full coil that can cost hundreds of millions of euros.
So how does simulation then fit in this development process of this coil?
I mean, the simulation for coils, superconducting coils, are everywhere. Is integral part of the development process. We are talking about electromagnetic simulation, thermal simulation, and mechanical simulation. Electromagnetic, because we are talking a very high current on a very complex shape. So we use it to for example, to extrapolate the magnetic field and the electromagnetic forces that act on the material surrounding the coils and between the coils. These electromagnetic forces generate huge stresses, can generate huge stresses on the material. And so you have to you use them in simulation to build the intercoil structure to withstand this giga-newton of forces. And then the thermal analysis. I mean, I told that we are working very low temperature, and when you cool down material from room temperature to 20 Kelvin, the property of the materials change. There is thermal contraction, so there are stresses also generated for all this process, and in this, which has to be evaluated. And at the same time, you have to simulate the cooling process. So all the pipes necessary to the cooling, the helium flow, because we use helium gas or liquid helium, depending on the material, to cool down the magnets. And finally, another fundamental simulation is for the quench protection. So the superconductors are very powerful material because they work at zero resistance, so allows you to generate very high field with very high current. But if something happened to the superconductivity and you have the change of status from superconducting to normal, you suddenly have a region of the magnet that is not superconductive, is normal. So there is a huge heat produced in a local spot, and you have to detect it quickly and to extract the power for the coil from the coil in order to protect it and avoid damages due to mostly to the quick heat of the material that can generate deformation or even melting the material, considering the huge energy stored.
So indeed, sounds like there's quite demanding simulations to be done, and that the role is very important there. Then I guess the key question is, as sort of suggested by the name of the podcast. So what is the state of simulation in the field right now? So are the tools and processes able to meet the high requirements?
I mean, of course, in the last 20 years, there was a huge improvement in the simulation capabilities for complex systems, especially for multiphysics. But there is always the desire to improve these capabilities and to increase the complexity. Ideally, you can run the full power plant, cooling down, charging of the coil, and to see how the forces are distributed, how the stresses are distributed inside the coils, even at cable level or even smaller level. But of course, this would be extremely demanding. So one of the first things that you try to do is to simplify this type of simulation in order to not have an extremely long time of computation, and increasing in complexity during the design process in order to study specific region, location, or condition that you are progressively discovered to be critical. There are many challenges. Ideally, as I said, you do full domains simulation with all the domains, electromagnetic, thermal, and mechanical. But of course, you can always try to decouple these elements and find a simpler simulation, a lighter simulation. But you cannot go below a certain amount of volume of computational power, let's say.
So a question we've asked on this podcast is about this famous magic wand. So if you had a magic wand and you could just one thing improve in your current simulation processes or workflows, would I be right to assume that for you it would be the ability to run these very complex full-sized simulations?
Yes, I think yes, it would be, but fortunately, I would say for our present status, this is not something that is immediately necessary, because we are Gauss Fusion is a young company, and we are progressing in our design, starting from a simplified system and increasing complexity, as I was saying. So I think it's something that in the future will be very useful, and for the future, I would say within 3, 4, 5 years, when we will have a very detailed design and where we will have to study the technical details of the final layout of the power plants. There, to be able to have an multiphysics complex, complete simulation will be very helpful to benchmark our design. Yes.
So how does it work? Like how does the workflow look like in general? So when it comes to basically manufacturing these very complex designs and these magnets, so what does the workflow or the process look like?
So let's take an example that is the demountable coil development program. It's something I'm directly involved, and it's something quite new for the superconducting coil. So basically the core element of the demountable coil is the demountable region, so the joint where you connect two cables together. So you start studying the single connection with electrical simulation to study the resistivity, the resistance of the interface between the two. Then you build a single joint test connection, and you benchmark your simulation with the experiment of the single joint. From the information you discover there, you go on a bigger scale. So the next step is a mock-up where you have the stainless steel support of the joint, like in a real conductor, in a real coil. And you have multiple joints that has to work all together. They have to be well connected, well aligned. And so you start to develop, to study also the mechanical support structure together with the joints. And you do the mechanical study of how the stress behave in the interface, in the coil plate for the support structure. And with the experiment, you check your simulation, your expectation, and you tune it again. You improve your simulation because, of course, they are not perfect. They have to be tune on your design, on the material, and all the small variables that you discover along the way. And at that point, you design a model coil. So a coil that is half the scale of the final one in the power plant. You produce it. After you make the best design possible, you produce it, you test it, and you benchmark the intermediate simulation. And at that point, you have enough information on how these complex systems really behave in order to be fairly certain. Then when you will produce the final coil, it will work as the simulation have predicted.
So what kind of technologies do you see, like emerging technologies, do you see helping you do this in the next, let's say, year, 2 or 3? So that emerging technologies that will help you do what you do, but just better or more efficiently.
If we are talking, I mean, it's a very complex question, of course. If I knew already what will appear in 2-3 years that can help me now, it would be a huge help in the process. But I think one point for sure is that the potential that the machine learning and artificial intelligence is unlocking and is improving constantly will provide us with support. There are these physics-informed neural networks that I think they can have big potential for this type of analysis, especially when you are trying to extrapolate from a small scale to a big scale, and which is something very complex, because if something has never been realized before in such a scale, there are elements that you cannot know. So you have to trust your extrapolation, your simulation. And if you have and I think in this field, combined with the classic finite element model, also this physics-informed neural network could provide a good support. And of course, as we were mentioning, the increase of computational power. That is something that is always useful.
All right. Yeah, I guess we have asked this question many times from different guests on what kind of technologies. At this point, we could almost rephrase the question as, how will AI help you in the future?
Yeah.
Since artificial intelligence, machine learning seem to be the thing, no matter the industry. So it's interesting to hear that, and at the same time, not surprising to hear that it is exciting for you guys as well.
And I think from the fusion point of view, more in general, especially from magnet confinement, I think there is a huge attention to the option of demountability of the coil. Gauss is not the only company looking at it. I think we are looking at the demountability on a bigger scale than other fusion companies. And I think that will be one of the key technology for really make fusion industrialized.
Well, I guess the last question could then be on, since there is this age-old joke, how fusion energy is always 20 years ago or 25 years in the future, I mean.
Yes.
So what kind of signals or what kind of news should our listeners be keeping an eye on to get a signal that there is actually something to happening or some sort of real progress being done?
Yeah, that's yes, it's a very common joke that fusion is always 20 years far from now. But I think key signals and be to have the news of successful testing of enabling technology, like the work we are doing. And also, I think it's very important signal to see the private and public funding that has been released in the last year and probably will be released also in the future to support our work in general as a fusion community. Because basically it's very challenging to do this without public support because of the large cost involved in fusion power plants and in all the development and preparation to operation. And I think that the commitment that the politics and funding system is giving to the fusion environment is a proof that everybody's thinking that technology is mature enough to achieve this goal within the next 15 to 20 years. For real.
For real this time. All right. Well, thank you, Tommaso. This was awesome. Thank you so much for joining.
Thank you very much for inviting me.
Thank you for listening to this episode of The State of Simulation. To stay updated with the latest episodes, webinars, blogs, white papers, and more, join our community of more than 7,000 engineers and engineer-minded people on our LinkedIn page, Quonscient. Thank you again, and see you in the next one.